Think about it. Sidewalks, bridges, dams, entire cities are built with it. Concrete is literally the most used substance on Earth, right after water. We see it everywhere, every single day, but do we ever really stop to think about what it is? I mean, it starts as this wet, gray slurry, and then it becomes, well, artificial rock? So how does that happen? What's the secret sauce? Let's dive in and break down the chemistry.
Okay, so how does a simple powder turn into something as solid as rock? I think most of us, if we had to guess, would say it just dries out, right? Kind of like mud caking in the sun. But here's the thing. If that were true, how could concrete possibly harden underwater? Which, by the way, it totally can. The real story is so much cooler and way more active. It's not drying at all. What's really happening is a chemical reaction. When you add water to cement powder, you're not just making some gray mud, you're kicking off a powerful, complex chain reaction called hydration. This isn't a passive thing like water just evaporating. No, this is an active process of creation, of building something new from the molecules up. And that is the entire secret to concrete's incredible strength. All right, so let's get into it. To really get what's going on, we need to meet the main players in this little chemical drama. They're all hiding inside that simple gray powder we call cement. So think of this like a cast of characters. First, you've got the silicates, C3S and C2S. These are your workhorses, the slow and steady builders. They're the ones who are going to give the concrete its real long-term durable strength. Then you've got this other one, tricalcium aluminate, or C3A. This guy is a total loose cannon. It's super reactive and just wants to set the whole thing instantly, which would be a disaster. And that's where our hero comes in. Gypsum. Gypsum is the controller, the manager who steps in to make sure C3A doesn't just ruin the whole party before it even starts.
Okay, let's zoom in on the very first moments. The instant water hits that cement powder, the clock starts ticking. It's a full-on chemical race, and the stakes could not be higher. If everything goes right, you get strong, solid concrete. But if it goes wrong, you're left with a useless, crumbly pile of junk.
So just imagine for a second there's no gypsum in the mix. We'd have a massive problem. That super reactive aluminate, the C3A, would go wild. It would react with the water almost instantly in something called a flash set. It throws off a ton of heat and creates this really weak garbage structure. We're talking about the concrete hardening in the mixing truck before it even gets to the construction site. It'd be totally useless. So gypsum's job is to jump in immediately and get that C3A under control to prevent this disaster.
And what does that controlled reaction create? Well, it forms the very first solid thing in the mix, a compound called ettringite. Picture these tiny microscopic, needle-like crystals starting to form everywhere. This is so critical. This formation is basically buying everybody else time for the real strength-building reactions to get going. But, and this is a big but, these little needles are just a temporary fix. Now, here's where things get kind of weird. The rhythm of this whole reaction is bizarre. You have this initial flurry of activity, ettringite is forming, things are happening, and then the whole system just pauses. It goes dormant. For a few hours, it seems like nothing is happening at all. This is called the dormant period, and thank goodness for it. It's the window of time that gives construction crews a chance to pour the concrete and smooth it out before it turns into a giant rock. And then just as mysteriously as it stopped, the main event kicks off, and the concrete really starts to harden.
So that begs the question, right? Why? Why on earth would this super powerful chemical reaction just take a coffee break? It's been a real puzzle for scientists for a long time, but the leading theory is pretty fascinating. So the theory goes something like this. Those very first things that form, like the ettringite needles, create this incredibly thin barrier around the cement grains that haven't reacted yet. It's like they're putting up a temporary little shield. And this shield blocks the water from getting to the rest of the cement, which basically just pauses the whole reaction. Then, after a couple of hours, that fragile barrier starts to break down, it shatters, and whoosh, the water can rush back in and kickstart the main event, the real strength-building phase. Pretty clever, right? And that brings us to the main event. The dormant period is over, the shields are down, and now it's time for our workhorses, the silicates, to finally get to work. Their job is to build the microscopic structure that is going to give concrete its legendary strength. And what do they build? This stuff. Calcium silicate hydrate, or CSH for short. Now, if ettringite was the temporary scaffolding, CSH is the actual steel-reinforced foundation of the whole building. It's not some neat, tidy crystal. It's this messy, complex, gel-like substance, and it is hands down the single most important ingredient for strength. This is it. This is the microscopic superglue that holds the entire thing together. And what's really amazing is how it builds itself. It's a two-pronged attack. First, the CSH gel starts to form on the outside of the original cement particles. But then, it also starts growing from the inside as water manages to seep through that outer layer to react with the core. So you've got this process happening from the outside in and the inside out at the same time. It creates this incredibly dense, tangled, interlocking web, and that's the real secret to its phenomenal strength. But wait, the story isn't over. Not even close. Even after the concrete is hard enough to walk on, the chemistry is still chugging along. These transformations keep happening for weeks, months, sometimes for years. And understanding what happens in the long run, well, that can be the difference between a building that stands for centuries and one that fails catastrophically. Remember that ettringite we talked about, the initial scaffolding? Well, turns out, in your everyday Portland cement, it's not meant to last forever. Over time, as the chemistry inside the concrete continues to shift, those needle-like crystals slowly dissolve, and then they reform into something else, a more stable, plate-like crystal called monosulfate. Now, this is totally normal. It's an expected, healthy part of the concrete's life. So that transformation is fine. It's all part of the plan. But what happens if the stuff you form in the beginning is fundamentally unstable? What happens when the chemistry goes wrong from the start? Well, there's a tragic, real-world example from post-World War II Germany that shows us exactly why getting this deep chemistry right is so critical. See, in the rush to rebuild after the war, a lot of construction used a special kind of fast-setting cement. It was called high aluminous cement. And at first, it seemed great. The concrete was super strong, really fast. But then, about 15 or 20 years later, disaster struck. These buildings started to collapse. The strength of the concrete had just vanished. So what on earth went wrong at the chemical level? Here's the fatal flaw. The initial crystals that formed in that special cement were metastable. Just think of it like something that's solid, but it's in a really fragile, temporary arrangement. It's not happy where it is. So over many years, those crystals slowly, inevitably shifted into their true, stable form. The problem? When they rearranged, the new structure took up less space. It created millions of new microscopic holes inside the concrete. This huge increase in porosity, basically empty space, caused the strength to just completely plummet. A tiny change at the crystal level led to a full-blown catastrophe. And that cautionary tale is precisely why understanding this chemistry is so unbelievably important. It's not just some academic exercise. This knowledge is what lets us engineer the concrete we use today to be safer, to last longer, and even to be more sustainable. Because we understand this now, we can fine-tune the chemistry to solve all kinds of problems. Think about pouring a massive dam. That reaction creates a ton of heat, which could crack the whole thing. So we can slow the reaction down. Or we can design cements that can resist chemical attacks from things like sulfates in the soil, which could literally eat the concrete from the inside out. And, maybe most importantly for today, we can blend in things like fly ash from power plants to make concrete with a way smaller carbon footprint. I mean, just look at the difference this makes for heat. The chart shows it plain as day. By simply replacing some of the regular cement with fly ash, you can dramatically lower that initial spike in temperature. It's a simple chemical tweak, but it's what prevents a giant structure like the Hoover Dam from cracking itself apart as it hardens. We're talking about control at the molecular level, having a massive, real-world impact. All right, so let's just quickly recap the big ideas here. First, and most importantly, concrete hardens because of a chemical reaction, not because it's drying out. Second, that whole process is a carefully controlled race against time, with gypsum playing traffic cop for the superfast reactors. Third, the real hero of strength is that microscopic glue, the CSH gel. And finally, understanding how all this stuff behaves over decades isn't just interesting, it's absolutely critical for safety and for building things that actually last. It really makes you look at a simple sidewalk differently, doesn't it? Concrete seems so basic, so inert, but it's really this dynamic chemical system that's still evolving years after it was poured. And it makes you wonder, now that we can control this chemistry with such incredible precision, what's next? What new superpowers can we give the world's most used material? Self-healing concrete that fixes its own cracks? Concrete that actually absorbs CO2 from the atmosphere? The future of the stuff that builds our entire world is still being written, one molecule at a time.